Good morning once again. This is SK Ghosh. I would like to welcome you to our web seminar today on seismic detailing of special shear walls and coupling beams. I'm pretty sure most, if not all of you, attended our web seminar yesterday, which was on seismic detailing of reinforced concrete moment frames. Between yesterday's seminar and today's seminar, we will have covered the entire seismic detailing requirements of ACI 31808 and BNBC 2020. Yesterday, as you would recall, we had uh, problems with our internet connection. We lost quite a bit of time. We have taken measures today which hopefully will keep that from happening. So I'm hoping for a smooth seminar, in which case we may have time at the end for question and answer. The first few slides are the same as I showed yesterday. And you will understand why. So the detailing that we will discuss is in accordance with BNBC 2020, which I kind of said already. BNBC 2020 was gazetted on February the 11th, 2021, at which point it became official. The concrete and seismic concrete design provisions, including seismic detailing requirements of BNBC 2020, are based on those of ACI 31808 edition. And that is kind of significant. I also mentioned yesterday that ACI has gone through 3 more editions since the '08 edition was published. So there was 31811, 3 years later, then 31814, and then the latest is 31819. In each of between 31808 and 11, there was at least one change that we will discuss at the very end of today's seminar. In 31814, there were major changes to shear wall detailing requirements that I have decided to bring into this seminar, and you will see that those are kept very separate. 31819 has further changes that are kind of complicated changes, and I have decided not to go there. It's for you, I think, a long time away, and too many other editions are probably, I'm pretty sure it is confusing. So we will keep to 31808. In one or two cases, I will indicate changes that have happened in 31811 because they are particularly important. And in a different color, very clearly indicated, I will show you 31814 changes because they are pretty comprehensive changes. And I think it will be good for you to be aware of them. As I mentioned yesterday, the seismic detailing requirements in ACI 31808 are in Chapter 21. But then when we do design or detailing by Chapter 21, the rest of 318 does not go away. The rest of 318 remains applicable unless something in there has been modified in Chapter 21 of ACI 31808. There are things that we do modify in Chapter 21, in which case the modified version applies. Whatever is in the main body does not apply. This data obviously Forgot to change. BNBC 2020 Part 6 is on structural design. Chapter 8 is on detailing of reinforcement in concrete structures. 8.3 specifically is earthquake resistant design provisions. So the shear wall detailing requirements that I will present to you today are to be found in section 8.3, which is part 2, chapter 6 of BNBC 2020. Now, just as when we detail or design by chapter 21 of 318, the remainder remains in effect. When we design or detail by section 8.3, chapter 6 of BNBC 2020, which is strength design of reinforced concrete structure, it remains applicable unless something in there has been specifically modified in section 8.3. This is kind of important. I didn't have a similar slide yesterday because I pretty much kept to the 2008 edition of 318. Anyway, all section numbers that are not in blue are from ACI 31808. I should have said blue or green. All section numbers in blue are from BNBC 2020 Part 6, Chapter 8 or Part 6, Chapter 6, unless otherwise noted. ACI 31814 changes are indicated in green. So keep that in mind. Blue is BNBC and green is 31814. This slide says things that I have gone over with you in earlier lectures, but this is very basic. So I think this is a good starting point. Seismic design, in its very essence, is an exercise in trade-off between strength and inelastic deformation capacity. I have said it again and again, and I'll come back to this statement. Inelastic deformation capacity is the ability of a structure to continue to carry full factor gravity loads as it deforms beyond the stage of elastic response. Elastic response, as I mentioned, doesn't have to mean force proportional to displacement. There is nonlinear elasticity, but elastic response does mean that it will have no residual displacement after the earthquake passes, no damage to repair. Okay. So that is elastic response. And we are saying inelastic deformation capacity is the ability of a structure to continue to carry full factor gravity loads as it deforms beyond the stage of elastic response. Inelastic deformation capacity comes from proper detailing of the structural members and the joints. So it is a trade-off. We can design for high strength and low inelastic deformability, or low strength and high inelastic deformability, or medium strength and medium inelastic deformability. Chapter 16 of the IBC, which would be part 6, section 2.5 of BNBC 2020, sets the design force level or strength. Okay, so when we say we set it, the code tells us the force level that we need to design for, depending upon the structure we are designing, the seismic hazard at the site of the structure, and so forth. Detailing rules are given in the materials chapters, which is chapter 19 of the IBC. This 19 should not have been blue. Anyway, it's part 2, chapter 8 of BNBC 2020 for concrete. Chapter 21 of the IBC for masonry, it's part 2, chapter 7 of BNBC 2020. Chapter 22 of the IBC for steel, it's part 2, chapter 10 of BNBC 2020. Chapter 23 for wood is part 2, chapter 11 of BNBC 2020. The materials chapter reference material standards. For concrete, the standard is ACI 318. So you go to chapter 19 of the IBC, you don't find a lot of provisions there because you are simply referred back to ACI 318. Three levels of detailing are defined in uh, uh, our codes and standards, including ACI 318: ordinary, intermediate, and special. The R value, which is in the denominator of the design base shear equation. The design base shear is a measure of the strength that we are building into a structure. Okay. The R value provides the link between the design force level and the level of detailing. The higher the R, the lower the design force level, the higher the need for fancy detailing, the lower the R, the higher the design force level, and the lower the need for very refined detailing. Now, having said seismic design is an exercise in trade-off between strength and inelastic deformation capacity, our codes do not allow us an unrestricted trade-off. If your seismic design category is A, which you do not even have in Bangladesh, no seismic design is required, so a question of trade-off does not arise. Seismic design category B is the only seismic design category where we are allowed unrestricted trade-off between strength and inelastic deformability. In seismic design category B, we need only an ordinary moment frame of concrete, for instance, which has an assigned R value of 3. If we want to benefit from a higher R value, lower strength level, we can go for an intermediate moment frame, which has an R value of 5. If we want to use even a lower strength level, we can go for an R of 8 and a special moment frame. All those choices are allowed. However, in general, going for a higher R and more complicated detailing is a more expensive proposition. It doesn't pay off. You are better off with higher strength and a lower level of detailing. In design category C, the minimum detailing required is intermediate detailing. You do not have the choice of going for an ordinary moment frame anymore and taking the penalty of an R of 3. That is not allowed. So if your design category is C, your choices are an intermediate moment frame with an R of 5 or a special moment frame with an R of 8. And you will typically find the intermediate moment frame solution is more economical. If the seismic design category is D or F, you do not have E or F in Bangladesh, so it is D. If your design category is D, then you, as a minimum, just must provide special detailing. So now your only choice is a special moment frame with R of 8. Now I said moment frame, it could be shear wall. Anyway, you get the point. It's not unrestricted trade-off. It is unrestricted only in design category B. If you are in design category C, the lowest level of detailing that is allowed is intermediate. If your design category is D, then the lowest level of detailing that is allowed is special. You do not have a choice of going to intermediate or ordinary detailing and take the penalty of lower R values. Now, shear walls can be used in bearing wall systems, building frame systems, or dual systems. And dual systems are of two kinds. in AC7 and BNBC, dual systems featuring intermediate moment frames and dual systems featuring special moment frames. Okay. So in a couple of slides, I have reproduced the rows in AC7 table 12.2-1, which is BNBC 2020 table 6.2.19. The rows where the reinforced concrete shear wall is featured. Yeah. So this whole page is bearing wall systems. If we have special reinforced concrete shear walls as part of a bearing wall system, R value is 5. And if we have ordinary reinforced concrete shear walls, R value is 4. There is no intermediate reinforced concrete shear wall recognized in our codes and standards. There is an intermediate shear wall that is precast, but we will not go there. We are not discussing precast. It is not mentioned in BNBC 2020. Okay? So I would like to point out that this pipe for a special reinforced concrete shear wall is significantly lower than an R of 8 for a special reinforced concrete moment frame. That is because a shear wall, even with special detailing, cannot be made as inelastically deformable as a reinforced concrete moment frame with special detailing. So there is that difference. Anyway, special reinforced concrete shear wall 5 and ordinary reinforced concrete shear walls an R of 4 in AC 705 as well as BNBC 2020. When a special shear wall is part of a building frame system, and I discussed the structural systems with you on an earlier occasion, I will not repeat. We don't have time for that. So now the R value is 6, and for an ordinary reinforced concrete shear wall, that is part of, or for a better way of saying it, for a building frame system featuring ordinary reinforced concrete shear walls, and R value is 5. Dual system with special moment frames that have special reinforced concrete shear walls, R value is 7. That is the highest you can get. And if the dual system with special moment frames has an intermediate reinforced concrete shear wall, R value is 6. Dual system with intermediate moment frame, if it has special reinforced concrete shear walls, R is 6.5. Ordinary reinforced concrete shear walls, R is 5.5. Okay, so but this the dual system with intermediate moment frame has restrictions on applicability. In high seismic design category, in your case, D is the highest. 15 meters should be the height limit on the structural systems. And the dual system with intermediate moment frames and ordinary reinforced concrete shear walls is not even permitted. Okay? So you have to look at these restrictions. Actually, this is about the only system where you will have to deal with restrictions. Well, I didn't quite say it right. The ordinary detailing, as I said, is not allowed in design category D. So when it is ordinary reinforced concrete shear wall, you would expect not permitted in design category D. You see it here, you see it there, and you will see it on the earlier tables as well. Anyway, so that gives you an idea of the R values that we are dealing with. So for a special moment frame, R of 8. For a special shear wall, depending upon which structural system it is part of, R value varies between 5 and 7. 5 for a bearing wall system, 7 for a dual system with special reinforced concrete moment frames. Okay. Then the restrictions on materials, these are the same as we discussed yesterday. The same restrictions on materials apply when you construct special moment frames or special shear walls of reinforced concrete. Okay, so uh, I repeat, the restrictions on materials that we discussed yesterday apply to special moment frames of concrete. The same restrictions apply to special moment frames of special shear walls of concrete, as well as coupling beams that we will discuss today and wall piers that we'll discuss at the end of the seminar today. So the same restrictions, so I will go over them quickly. The concrete compressive strength cannot be any lower than 3000 psi. No upper limit on the strength of normal weight concrete. That is significant. Lightweight concrete, we cannot have strength higher than 5000 psi, because for higher strength lightweight concrete members, we simply do not have test results under reverse cyclic loading. Reinforcement, the preferred type is A706, which comes only in grade 60 or 420 in MPa. Alternatively, ACI 318 allows the normal A615 belay steel, grade 40 and 60, with supplementary requirements. I said within parentheses modified. BNBC 2020 allows the same A615 grades 275, which would be 40 KSI, and 420, which would be 60 KSI, with supplementary requirements. But BNBC also allows Bangladesh standard ISO 6935-2 grades 300, 350, 400, and 420. I understand that quite a bit of that reinforcement is used, but anyway, so that's the only difference between ACI 318 and BNBC 2020. This Bangladesh standard reinforcement is allowed in high seismic applications. The supplementary requirements for A615 belay steel for high seismic applications. These we also went over yesterday. The actual yield strength shall not exceed the specified yield strength by more than 18,000 psi. Upon retest, you can go another 3,000 psi, but that is the maximum allowed. This retest requirement was in 31805. I didn't find it in 31808. This is why I put it in blue. It is part of BNBC 2020, though. You have that in there. This, as I mentioned yesterday, is an extremely important supplementary requirement. This requirement is already part of ASTM A706. But A615, this is a supplementary requirement for seismic applications. This is important because in seismic applications, more is not better. If you have higher yield strength in your reinforcement than you specified, the member reinforced with that steel will have higher flexural strength than you counted on. That member will attract higher shear forces to itself in an actual earthquake situation. You will not be correspondingly increasing the shear strength of the member, thereby making brittle shear failure more likely. And that is not good. Okay, so this is why this is an important requirement. Minimum elongation of A615 reinforcement must be the same as that of A706 reinforcement. That's what this amounts to. This was not part of 31808, but this has since been added in ACI 31814. We have added that. And finally, the ultimate tensile strength must be the measured ultimate tensile strength shall be no less than 125% of the measured yield strength of the reinforcement. Okay? So, three supplementary requirements. The actual yield strength shall not be greater than the specified yield strength by more than 18,000 psi. The elongation over an 8-inch gauge length must be the same as that for A706 reinforcement, and the tensile strength to yield strength ratio shall not be any less than 1.25. The value of FYT, yield strength of transverse reinforcement, used for confinement purposes, shall not exceed 100 ksi. So we are allowed up to 100 ksi yield strength of transverse reinforcement, high seismic applications. However, when the transverse reinforcement is shear reinforcement, you cannot use in computations a yield strength higher than 60 ksi. That's what the second and the third requirement on the slide tells you. If we allow shear computations based on higher yield strength, then we'll be looking at wide shear cracks, which are very objectionable. So this is why the restriction. But for confinement purposes, we are allowed up to 100 ksi yield strength of the transverse reinforcement. And yesterday I explained why that is very significant indeed. So now we come to the design of special shear walls for shear. We have to design every structural member for, well, if it is a column or a shear wall, we have to design it for shear. We also have to design it for combined flexure and axial load. Okay, so we typically with shear walls, we design for shear first, and then we proceed to designing for flexure and axial load, which will come after we are done with shear. Now, this is the first significant green that you see in my slide set. Green, remember, is 31814. Requirements for special shear walls significant ways in ACI 31814 in view of lessons learned from the Chile earthquake of 2010. So the shear wall requirements of ACI 31808 that we are discussing today started in 31899 edition, 99 through 2011. The provisions remained essentially unchanged. We made maybe little changes here and there, but essentially unchanged. And then in 2014, very significant changes that are, how should I say, that cover many aspects of shear wall design. And as I mentioned, we will not go there today. In the 2019 edition, there is a further round of significant changes. Now, as in the design of any member, in the shear design of shear walls, the required shear strength vis-a-vis must be less than or equal to the design shear strength, the nominal shear strength vis-a-vis N, reduced by a phi factor, which is typically 0.75, although you will see that there is a complication there in the design of shear walls. We will discuss that with you. Very importantly, you saw yesterday that in the design of beams as well as columns of special moment frames, we design for the maximum shear that can develop in the beam or the column. In the case of shear walls, we do not do that. We basically are not able to do that. We cannot figure out even today with any degree of precision the maximum shear that may develop in a shear wall section in the event of earthquake excitation. So we design for V sub U coming from analysis of our structure under code prescribed seismic forces. This is very, very important. We are designing from shear obtained from elastic analysis rather than the maximum shear that can develop in our shear walls. That being the case, we try to play it safe with the phi factor. Phi normally for shear would be 0.75, but ACI 318 says, and this is repeated in BNBC 2020, if we are designing a shear wall that may fail in shear before it fails in flexure, the phi factor shall be 0.6 rather than 0.75. Okay. I paraphrased what is written here, but the way I said it is the way you should think. Okay, if a shear wall may fail in shear before it has a chance to fail in flexure, that shear governed shear wall shall be designed using a phi factor of 0.6 rather than 0.75, because we are not designing for the maximum shear that may develop in the shear wall. Now, which walls may fail in shear before they fail in flexure is not that easy to pin down, uh, uh, let us say analytically, but I will tell you that once you go, so let's say height, total height to total wall height, H sub W is ACI 318 notation, to total length L sub W ratio, H sub W over L sub W ratio of 1 or less, your shear wall will invariably fail in shear and not in flexure. Those are definitely shear governed shear walls. For the height to length ratios between 1 and 2, you as the engineer by the way you design and detail the wall may make the wall fail in flexure or in shear. But when the height to length ratio exceeds 2, your wall will fail in flexure, not in shear, unless you do something extraordinary like leave the horizontal reinforcement out or something like that. So height to length ratio beyond 2, you are looking at flexural failure preceding shear failure, in which case you do not have to reduce the phi to 0.6. I see a lot of people use P of 0.6 for all shear walls, even with height to length ratio of 5. That is a total waste of money. Okay, so beyond height to length ratio of 2, you are not required to, and you should not use a P of 0.6. If you don't feel comfortable with 2, maybe go to 2 and up to 2.5. But beyond that, it does not make any sense whatsoever to use a P factor of 0.6 in shear design. Now the V sub n. So V sub u we just talked about. It comes directly from analysis. V sub n nominal shear strength is the shear carrying area of the section, and that is clearly shown here. This is the total length of the shear wall multiplied by the web thickness. The overhanging flanges do not count when it comes to shear. That is important. That's the way we have always designed shear walls. So the V sub n is the shear carrying area of the shear wall A sub CV times the the two contributions to shear strength. Concrete contribution, alpha sub c times square root of f sub c prime, and the steel contribution rho sub t times f sub y. But let me put it this way. So concrete can carry, if you look through ACI 318, two square root of f sub c prime. In your units, I believe the number is 0.17 square root of f sub c prime. Concrete is always good for 2 square root of f sub c prime. But years ago, there were tests at Portland Cement Association of low-rise shear walls that showed if you have height to length ratio below 1.5, your shear wall can do better. That the concrete in your shear wall can carry more shear than 2 square root of f sub c prime. So since then, we have said that for height to length ratio of 1.5 or less, concrete is good for 3 square root of f sub c prime. For height to length ratio of 2 or more, concrete is down to 2 square root of f sub c prime. For height to length ratios between 1.5 and 2, we interpolate between 3 square root of f sub c prime and 2 square root of f sub c prime. Okay, 3 and 2 in our units, 2 is 0.17, 3 would be 0.25 or something like that. Okay, I should have had the metric equivalent here, but I don't. Anyway, so that is the concrete part. And then whatever concrete cannot carry, if V sub n is larger than, no, P sub u has to be no larger than phi times V sub n, okay? Or P times V sub n has to be at least equal to V sub u. So any part of V sub u that concrete alone cannot carry, if V sub u is larger than A sub c v times alpha sub c square root of f sub c prime, then we have to put in horizontal shear reinforcement, and rho sub t is the horizontal shear reinforcement ratio, the cross-sectional area of horizontal shear reinforcement divided by the thickness of the shear wall and the spacing of the shear reinforcement. Okay, so rho sub t times f sub y is the shear carried by the horizontal shear reinforcement. This is how we design the shear reinforcement in a shear wall. So concrete can carry alpha sub c square root of f sub c prime times a sub c v. If v sub u required shear strength is larger than that, then for the remainder of the shear, we provide horizontal shear reinforcement, however much is needed. And the shear carried by the horizontal shear reinforcement is rho sub t times f sub y, the horizontal shear reinforcement ratio times its yield strength. Now, once you have designed your horizontal shear reinforcement, ACI 318 and BNBC tells you that you will also have to provide so much vertical shear reinforcement, because it has been established by a lot of tests that horizontal shear reinforcement does not do you any good unless you also have vertical shear reinforcement. And we will look at all of that. There are also minimums on horizontal as well as vertical reinforcement that you will see. Now, there is an absolute upper bound on the shear that a shear wall can carry, and that is 8 square root of f sub c prime, except this part is a little bit complicated. You have to read the code. If the shear wall that we are talking about is part of a string of shear walls in the building, a part of a number of shear walls along the same line, then for all these shear walls, the limit is 8 square root of f sub c prime, which is what I have on the slide. But if you have an individual shear wall, then the limit is 10 square root of f sub c prime, a little bit higher, 0.83 in your units. This is because when the shear is very high, imagine a shear wall with a point lateral load applied at the top. When that horizontal load is very high, it will be transmitted to the foundation through diagonal struts that form within the shear wall. And those diagonal struts will crash in compression under high shear load, and no amount of reinforcement will prevent that compression crashing. Okay, so this limit is the upper limit. You cannot go beyond that. Okay, so shear design. Okay, the ratio. This is a detail that I'll let you read. These are very important. So minimum longitudinal reinforcement ratio, you have to have 0.25% longitudinal reinforcement, which would be vertical reinforcement in a shear wall, at a spacing not to exceed 450 millimeters. Okay, that's 14 inches, no, 18 inches. So minimum vertical reinforcement, 0.25%, maximum spacing 450 millimeters. Horizontal reinforcement also minimum 0.25%, maximum spacing 450 millimeters. You shall provide 2 curtains of reinforcement when V sub u, the required shear strength, exceeds 2 square root of f sub c prime. Okay. 2 curtains of reinforcement. ACI 31814 says, or when height is larger than or equal to 2. So from 31814 onwards, we have to provide 2 curtains of reinforcement in the taller shear walls, height to length ratio, taller and slenderer shear walls, height to length ratio larger than or equal to 2, irrespective of how much shear you are dealing with. Okay. So, but shear exceeding 2 square root of f sub c prime will trigger 2 curtains of reinforcement. Now, I would like to say that how do I want to put it? 6-inch shear walls, 150 millimeter, are probably the thickest that you should design with 1 layer of reinforcement. From 8 inches onwards, 250 millimeters, if you provide only 1 layer of reinforcement, you are keeping almost 4 inches of plain concrete outside of the reinforcement layer, and that's never a good idea. From 10 inches onwards, nobody I know has ever used 1 layer of reinforcement in a shear wall. That does not make any sense. And in high seismic applications, shear walls thinner than 10 inches typically do not work out. So 2 layers of reinforcement are automatic almost, although although there is a specific requirement. Now, importantly, when height to length ratio is less than or equal to 2, the shorter, stockier shear walls, the vertical reinforcement ratio must be no smaller than the horizontal reinforcement ratio. This is very, very important. So short, stocky shear walls, we figure out rho sub t, those are the shear governed shear walls. We figure out how much horizontal shear reinforcement we need, and then ACI 318 tells us that the vertical shear reinforcement we provide cannot be any smaller than that. Now, if the shear is less than 1 square root of f sub c prime. 0.8 in your unit, square root of f sub c prime. Then your horizontal reinforcement is shrinkage reinforcement. It's not shear reinforcement really. There is hardly any shear. And then those minimum requirements can be relaxed. 0.25% can be down to I don't remember, 0.2 or even lower, 0.18%, I think is allowed. This is now chapter 14 of ACI 318, your section 11.6. You take your minimum from that section. Okay, it's no longer 0.25%. This is a 318.14 commentary. When you see R in ACI 318, it is a commentary section. Uh, every other document commentary is C. In ACI 318, commentary is R. The idea is that the ACI 318 standard itself is a standard which eventually becomes code when adopted by jurisdiction. The commentary is a report from ACI Committee 318. It never becomes legal or code. Okay, and the R stands for report. Anyway, the commentary says the requirement for 2 layers of vertical reinforcement in more slender walls is to improve lateral stability of the compression zone under cyclic loads following yielding of vertical reinforcement in tension. Okay, now special shear wall design for flexure and axial compression. Yesterday I was quite confused about time. It's approaching 8:30 in Dhaka. So no, I have time. No, not a, I don't think it should be a problem today. Okay. This is the only time that I will take you back to 318.95, which was the 318 edition preceding 318.99, when I said the current shear wall design was first introduced. Okay. So back in those days, 318.95 and earlier, in designing a shear wall, what we had to do was to calculate. Let's look at this picture. So we used to take the factored axial load tributary to the shear wall. It is not the weight of the wall. This is all the load that we are dumping onto the shear wall. Okay. So factored axial load tributary to the shear wall, divide that by the gross cross-sectional area. That gives us a uniform compression across the shear wall section. Then we took the factored overturning moment at the base of the shear wall, okay, which should be caused by the code prescribed seismic forces. So factored overturning moment at the base of the shear wall divided by the gross moment of inertia of the shear wall section multiplied by half the length of the shear wall. That will give us the largest compression at one end, the largest tension at the other end, and if the compression due to axial load plus the compression due to the overturning moment, this plus that exceeded 20% of f sub c prime, 0.2 f sub c prime. Then we had to design our shear wall pretending that the web of the shear wall was not even there. The web did not do anything for us when it came to flexion and axial load. The web that carried all the shear did not do anything for us when it came to flexion and axial loads. We had to design the 2 boundary elements, the 2 column-like elements at the ends, to carry the entire factored axial load and the entire factored bending moment. Okay, so this column and that column have to be designed to carry an axial load of P sub u by 2, one half of the factored axial load, plus the factored overturning moment at the divided by the distance between the central lines of those boundary elements. So if the highest compression at the edge of the shear wall exceeded 20% of F sub C prime, each boundary element had to be designed for that much of axial load. This resulted in very large boundary elements with extremely large amounts of vertical reinforcement required, as you would imagine. And let me talk about the confinement with the let me go to the picture and then come back to the two slides. Okay. So this is a building we designed in the UBC days, quite some time ago. A concrete building, frames on the periphery, and there are L-shaped shear walls in the core. And the shear walls are boundary elements. I think the picture is pretty clear. It was back in those days seismic zones in the code. This was UBC seismic zone 4, 20-story tall building. The beam sizes are given, the column sizes are given, the walls are 300 millimeters thick. And when we designed this building under UBC 97 zone 4 seismic forces, we ended up with 38 by 38 inch boundary elements, 950 by 950. 38 by 38 inch boundary elements with 36 number 11 bars. Our number 11 means an inch and 3/8 in diameter. I don't know how many millimeters that is. Okay, an inch and 3/8. It is almost it's 15, 16 millimeters. So 38 by 38 boundary elements, each with 36 number 11 bars. So far, it is not good, but the actual nightmare is that these 36 number 11 bars had to be tied and cross-tied like column bars. Remember, every other bar laterally confined by the corner of a tie or a cross tie, maximum spacing center to center between any two supported bars 14 inches, and the maximum clear spacing between a supported bar and an unsupported bar 6 inches. So we were looking at one tie all around and then multiple cross ties in the two orthogonal directions. And this in a column had to be provided over the region of potential plastic hinging. In a shear wall, we had to provide this confinement until the combined compression due to P sub u and M sub u went down below 15% of F sub C prime. And that sometimes took 3-4 stories of a multi-story building. So shear walls back then were a very expensive proposition. The design procedure was such that the owner and the developer on the west coast of the United States learned to basically stay away from concrete shear walls. It was really that bad. And this is what was remedied by the design procedure that started in ACI 31899. Actually, that originated in the 1994 Uniform Building Code, if I want to be exact. So the shortcomings of 31895 requirements were the requirements resulted in very large boundary elements with extremely large amounts of vertical reinforcement required. extensive amounts of required confinement reinforcement made construction very difficult. So the constructability part was very poor indeed. Now, uh, what the constructability, I think everybody would appreciate right away. What was not uh, visible and what was not apparent until you thought about it is that all this reinforcement did not give us a good shear wall. We were cramming all this reinforcement into the boundary elements, the large boundary elements. So these shear walls that we were designing had enormous flexural strength, which would mean they would draw incredible amounts of shear to themselves in an earthquake. We definitely did not correspondingly increase the shear strength of the shear walls. There was no such requirement, making brittle shear failure more than likely. So unconservative shear design was the result of providing all this flexural reinforcement. So what looked like a very conservative thing was not even a safe solution. This was actually unsafe, unconservative. Okay, so ACI 31899 or before that 94 UBC, 97 UBC first said, forget about discounting the web of the shear wall. That does not make any sense. That was a throwback to the days when shear walls used to be infill frames and the infill used to go in an earthquake. Okay, now we have monolithic shear walls. So ACI 31899 said design a shear wall for flexion and axial load just as you design a column for flexion and axial load, the entire cross section being effective. And don't worry about slenderness effects or the fact that because a shear wall is a deep structural element, the strain distribution may not be linear. Don't worry about those things. Okay. So design a shear wall as you would design a column under flexure and axial load. This was a huge change from the past. Okay, some details. Effective flange width. If your shear wall has flanges, which typically is the case, effective flange width is half the distance to the next cross wall or 1/4 of the total wall height. Okay, whichever is the smaller of the two. So, or let me put it this way, the effective flange width is 1/4 of the total wall height, except that you cannot encroach onto the flange of the neighboring cross wall. Okay, you can go only halfway to the other cross wall. This is this is a whole lot. So it is very seldom that you will have to ignore any part of a physical flange that you have, whether anyway. So this is a very generous effective flange width. Now, very importantly, there are two ways of designing the there are two ways of figuring out whether we need specially detailed boundary elements in our shear walls. Okay. One is called the displacement-based approach. That's 21962 of ACI 318 8366B of BNBC. The other is the conventional approach that preceded the displacement-based approach, that is in 21963 and 8366C of BNBC 2020. The displacement-based approach is not applicable to all walls. It is applicable to cantilever shear walls hinging at the base. This is the best way to think. Okay? I will show you the The 318 language is on the slide, but we are basically talking about cantilever shear walls hinging at the base. So displacement-based approach is applicable to walls or wall piers that are effectively continuous from the base of the structure to the top of the wall. So it hinges at the base, not somewhere in the middle where the section changes all of a sudden. And designed to have a single critical section for flexure and axial loads. Okay. Again, cantilever shear wall hinging at the base. ACI 31814 has said the height to length ratio in addition has to be larger than or equal to 2. So the displacement based approach will not apply to shear governed shear walls. It will be only to flexure governed shear walls. This is 31814. Now, this is the crux of the whole thing, and please listen to me very closely. So I made a statement that starting with 31899, when we design for flexure and axial loads, we do not make any distinction between a column and a shear wall. That is fine. That is well and good. But practically looking and speaking, there is a huge difference between a column and a shear wall. The difference is almost the entirety of a column section is tightly confined. If you leave aside a relatively thin cover, the rest of the column section is tightly confined by our code requirements. A shear wall section that may be 30 foot long is very difficult to tie and cross tie like a column section. That would be awfully expensive, time consuming, and so forth. But more importantly, if we were to do that, if we were to tie and cross tie the entire cross section of a 30-foot long shear wall, much of the time and effort and money would be wasted because we do not have significant compression over much of the shear wall cross section. So if we don't have compression, what would all this confinement do for us? The answer is nothing. So ACI 31899 said, and we still say in 318, you shall specially confine only those parts of a shear wall cross section that develop significant compression. Okay, I repeat, you shall specially confine only those parts of a shear wall cross section that develop significant compression. Now, how do we figure out the portions of the shear wall that develop significant compression? So that's where ACI says compute your neutral axis depth. If the neutral axis depth C is larger than or equal to a critical neutral axis depth, which is the right-hand side of the expression you see on the slide, then a part of your cross-section is under significant compression, and we have to specially confine it. If the calculated neutral axis depth is less than the critical neutral axis depth, you do not need specially confined boundary elements, period. Okay? Now, when the neutral axis depth exceeds the critical neutral axis depth, we do not confine the entire cross-section from the extreme compression fiber to the neutral axis depth. We confine most of it, but not all of it, because we don't have significant compression over the entire compression zone. How much we confine, you will see in just a little bit. But I hope all of this makes sense. Okay. So if neutral axis depth goes beyond a certain value, we specially confine most of the compression zone, the distance from the extreme compression fiber to the neutral axis. Okay. Now, the right hand side has L sub W, which is the length of the shear wall, a constant 600. Forget about the green for now. Delta sub U divided by the height of the shear wall, H sub W. This delta sub U is design displacement. Total lateral displacement expected for the design basis earthquake. That's what ACI 318 says. Now, let me tell you in practical terms what delta sub U is. So you elastically analyze the building of which the shear wall is a part under code prescribed seismic forces. That will give you a deflection at the top of your shear wall. That deflection amplified by the C sub D, deflection amplification factor for the structural system of which your shear wall is a part, is the delta sub U. So this is the displacement at the top of your shear wall caused by the code prescribed seismic forces amplified by C sub D. That's delta sub U. Okay. So now we know everything on the right hand side. There is a stipulation that if delta sub U over H sub W is very low, your shear wall is very stiff, we will not take it any lower than 007 for computation purposes. Now, ACI 318.14 has injected the 1.5 factor in the denominator, thereby requiring many more shear walls to have specially detailed boundary elements. Okay, the the let me not go to this 318.14 requirement. Uh, you will not be using it. You should not be using it. This is not your code. I just wanted to give you an idea of what is coming in the future, and there will be ample time to explain why this was done before that time. Okay, so let's stay without the 1.5. Now, the neutral axis depth. Neutral axis depth is distance from extreme compression fiber to neutral axis. That doesn't help you. The problem is neutral axis depth depends on the axial load sitting on your shear wall. The larger the axial load, the larger the axial compression, the larger the neutral axis depth. In the extreme, if there is no bending moment, only axial compression, the neutral axis depth is infinity. There is no, the entire section is under compression. So what neutral axis depth do we calculate? And I have a couple of slides that let me explain what those slides say with this figure, which I think is very good. So we are checking whether our neutral axis depth is larger than or equal to a critical neutral axis depth. So if we have a variety of axial loads on our shear wall to deal with in design, we would like to, for the purposes of that check, we would like to have the largest neutral axis depth. Whichever axial load produces the largest neutral axis depth is the load combination that we should consider. Okay, you see what I'm saying? If we want to see if something is larger than something else, We would rather like an upper bound value of the thing that we are checking. Okay. So in seismic design, we have two load combinations to consider: the additive seismic and the counteractive seismic that I've been talking about, it seems to me, for a long time. Okay. The additive seismic load combination will always give you a higher axial load than the counteractive seismic. I do not know that there is ever any exception to that. So that is the larger the axial load, the larger the neutral axis depth, remember? So we must calculate our neutral axis depth under the additive seismic load combination. That's where our P sub u will come from. Yeah. And then there is a factored bending moment corresponding to P sub u, which is M sub u. Do we calculate our neutral axis depth for the P sub u, M sub u combination? The answer is no. We are required to calculate our neutral axis depth for P sub u and the corresponding nominal moment strength at the critical shear wall section at the base. So we calculate C under P sub u coming from the additive seismic load combination and the corresponding nominal moment strength at the critical shear wall section at the base. Okay, so P sub u, M sub n. That neutral axis depth exceeding critical neutral axis depth will trigger specially detailed boundary elements. Now, when special boundary elements are required by the displacement-based approach, the special boundary element reinforcement needs to extend vertically. So how far do we go vertically with this special confinement? And the answer is L sub W, the length of the shear wall. If you have 20-foot long shear wall, we go 20 feet along the height. Or the factored bending moment at the base divided by 4 times the factored shear at the base, whichever is the larger of the two. Okay, so L sub u or M sub u divided by 4 times V sub u, whichever is the larger of the two. That is the vertical extent of special confinement that we must provide. The same extension of reinforcement is required below the critical section, except at the base of the shear wall, which is addressed in another section. So at the base, the special confinement goes at least 12 inches into the foundation. That is the vertical extent of special confinement. Horizontally, how far do we go from the extreme compression fiber towards the neutral axis? The answer is 1/2 of the neutral axis depth, or the neutral axis depth minus 1/10 of L sub W, whichever again is the larger of the two. 1/2 of the neutral axis depth or neutral axis depth minus 1/10 of the length of the shear wall, whichever is the larger of the two. In flange sections, boundary elements shall include the effective flange width that we talked about and shall extend at least 300 millimeters, 6 inches into the web. And when we say 6 inches into the web, that is from the flange web interface, not from the edge of the flange shear wall. Okay, so the entire shaded portion is specially confined boundary element. We so where was it? So the same extension of the reinforcement. So we said that the special confinement shall be provided along the height of the wall for a length L sub W or M sub W divided by 4 times V sub U, whichever is the larger of the two. The same extension of the reinforcement is required below the critical section except at the base of the shear wall, which is addressed in another section. And I said 12 inches into the foundation. That other section is here. Okay. So if the shear wall is sitting on anything but a foundation, then you go one development length of the largest longitudinal bar into that element. It could be a pedestal or something like that. If, however, the shear wall is sitting on a footing or mat or pile cap, which is the usual thing, then as I said, you go 12 inches into the foundation. ACI 31814 has brought back something we had in UBC 94 and 97, but was dropped in ACI 31899, which is a minimum thickness out of concern for out-of-plane buckling of shear walls, which had never been observed outside of the lab. But then in the earthquake in Chile 2010, and then the the two big earthquakes in Christchurch, New Zealand in 2011, we actually did see shear wall buckling, out of plane buckling of actual shear walls. So now the minimum thickness requirement was brought back. So the requirement is that in the specially confined boundary element region. Okay, you know what that is. That includes the flange, and you go half the neutral axis depth or neutral axis depth minus 1/10 of L sub W into the shear wall. And you also have to go at least 12 inches from the flange wave interface into the flange. So over that compression zone, the thickness of the shear wall shall not be any less than 1/16 of the unsupported wall height. 1/16 of the unsupported wall height. Now, in addition, I don't want to go through all of this. In addition, if your wall is not tension controlled, and the index of that is neutral axis depth is larger than or equal to 3/8 of L sub W, calculated neutral axis depth. If it is larger than or equal to 3/8 of L sub W, then there is no assurance that your wall is going to be tension controlled. And in that case, we have a 12-inch minimum on the thickness of the compression zone of the shear wall. Okay, so it is probably unlikely that you will go for a thinner web outside of the specially confined boundary zones. But anyway, technically, the minimum thickness applies to the specially confined boundary elements of the shear wall, not to the entire shear wall. So it is 1/16 of the unsupported height subject to a minimum of 12 inches if the minimum applies only for shear walls that are not necessarily tension controlled. This is commentary to the 12-inch requirement. A value of C larger than or equal to 3/8 of L sub W is used to define a wall critical section that is not tension controlled according to section such and such. A minimum wall thickness of 300 millimeters is imposed to reduce the likelihood of lateral instability of the compression zone after spalling of cover concrete. Pretty clear commentary. Now, this specially confined boundary element, boundary zone, whatever, what is this special confinement? So that's the subject of this section, we have a subsection that gives us configuration requirements, shape, arrangement, horizontal spacing, etc. Then another subsection that gives us maximum spacing along height of boundary element with one exception. And then a third subsection, minimum amount of transverse reinforcement with one exception. Anyway, I let me skip the word slides. I will let you read them at your leisure. So let me tell you that the main thing is, or the crux of it is, a specially confined boundary zone is essentially the same as the potential plastic hinge region of a special moment frame column. Let me check the time again. So we started at 7:30, 9 o'clock. So I have. Okay. So yeah, no problems. Somehow after yesterday, I'm kind of nervous. Okay, so yeah, we have time. I think it will work out today. So the specially confined boundary zone of a shear wall is essentially the same as the plastic hinge region of a special moment frame column. We provide the same confinement with just two exceptions. Okay, so a specially confined boundary element must be tied and cross-tied like the plastic hinge region of a column. Same requirements apply as before. So every other bar laterally supported by a corner of a tie or a cross tie, and the maximum spacing between any two supported bars of 14 inches. Okay. Now, there is a subtle difference between earlier edition between 318.14 and earlier editions of ACI 318, but we need not bother about that. 318.14 has added that the maximum spacing between any two supported bars shall also not exceed 2/3 of the boundary element thickness. So it shall not exceed 14 inches. It shall also not exceed 2/3 of the boundary element thickness. Okay? So, but that's 318.14. Now, I said that there are two exceptions. The shear wall boundary zone confinement is the same as the confinement of the hinging region of a column with two exceptions. One exception is here, the maximum spacing limitation for a column hinging region. The spacing of transverse reinforcement shall not exceed 1/4 of the minimum column dimension. Remember that 1/4 has been relaxed to 1/3 of the minimum dimension of the boundary element. This is the first exception. So in the case of a column, the spacing cannot exceed 1/4 of the minimum column dimension. In the case of a shear wall boundary element, the spacing cannot exceed 1/3 of the plane dimension of the boundary element. Okay. The rest is the same, 6 times the diameter of the smallest longitudinal bar and the S sub x or S sub 0, whatever that notation has changed over the years, which varies between 4 and 6 inches. The second exception is that in the case of a column hinging region, the minimum cross-sectional area requirement of the transverse reinforcement is given by two different expressions, and the larger amount governs. ACI 318 up to the 2011 edition exempted this first equation. Okay, that was the second exception. For shear wall bounded element confinement, we went by the second equation only. The first equation did not count. 318.14 has brought the first equation back, but that's into the future for you. So for you, the two exceptions are the spacing of transverse reinforcement shall not exceed 1/3 of the boundary element, minimum boundary element plan dimension, as opposed to 1/4. And the second exception is that the minimum cross-sectional area of transverse reinforcement is given by this one formula rather than two different formulas. 318.14 has brought this first formula back. Now, if you want to use the first formula, you will need to figure out the gross cross-sectional area and the confined cross-sectional area of the transverse reinforcement. That's where these commentary sections come in. Okay, with the help of this figure and the text of the commentary, you will be able to figure out the A sub G and A sub CH. I need not go there. This is 2014 stuff. Okay. So this is basically a summary of the displacement-based approach that we have discussed so far. Okay. So this is a shear wall subject to bending axial load shear, as they always are. If the calculated neutral axis depth, and we know which neutral axis depth it is under the P sub U given by the additive seismic load combination and the corresponding nominal moment strength of the shear wall section at the base. If that neutral axis depth exceeds the or equals the critical neutral axis depth, which is the right-hand side here, then we will specially confine a part of the shear wall cross section. How much of the shear wall cross section? Going from the extreme compression fiber, 1/2 of the neutral axis depth, or the neutral axis depth minus 1/10 of the length of the shear wall, whichever is the larger of the two. So this is the extent of the horizontal confinement. Vertically, we will go the length of the shear wall, L sub W, or the factor moment at the base divided by 4 times the factor shear at the base, whichever again is the larger of the two. Okay. So that's what we have discussed. There are no surprises here. The only reason I have two figures is those are the special bounded element transverse reinforcement in accordance with those ACI 31808 sections. If you are going with B and BC, those are your section numbers where you will find the confinement requirements. Now, the other approach where the displacement-based approach does not apply. The conventional approach, as I called it, this is not called that in ACI 318. It does not give it a name. This approach is applicable to any wall section. Special bounded elements are required as before, where the maximum extreme compression fiber stress exceeds 0.2 F sub C prime. So we go back to what we used to do. We calculate P sub U divided by A sub G plus M sub U divided by I sub G multiplied by 1/2 of L sub W. If that sum exceeds 20% of F sub C prime, then we provide that triggers special confinement. The specially confined boundary zone may be discontinued where the calculated stress drops below 15% of F sub C prime. 20% triggers it, but we cannot discontinue until we go below 15% of F sub C prime. Stresses are calculated based on factored forces using a linearly elastic model and gross cross-sectional properties. Okay. So, uh, so now the trigger is this combined compressive stress exceeding 20% of F sub C prime. This is not greater than or equal to, this is greater than. Okay. Now, I want to stress very emphatically that when we go back to the old trigger, the extreme fiber compression stress exceeding 20% of F sub C prime, we do not go back to neglecting the web of the shear wall in designing for flexion and axial load. We never do that anymore since 3/18/99. The entire shear wall section counts. Okay. So when that trigger goes off and we conclude that we must provide confinement over part of the shear wall section, the horizontally, what we confine is the same as in the displacement-based approach. So it is 1/2 of the calculated neutral axis depth or the neutral axis depth minus 1/10 of L sub W, whichever is the larger of the two. So even when we are using the conventional approach, we will have to calculate neutral axis depth. That does not go away. Vertically, we will discontinue the special confinement only when the combined compressive stress under P sub U and M sub U drops below 15% of F sub C prime, as I have said multiple times already. Okay. What is special confinement? I said that it is the same as what we provide in the hinging regions of special moment frame columns, with two exceptions. So this is that in picture. Okay. Now, first of all, I do want to make a point as made in the picture that a specially confined boundary element does not mean necessarily a thickened shear wall or a shear wall with a flange or a column at the end. No, it can be a rectangular shear wall, no thickening of the ends. The specially confined boundary zone is the specially detailed part of the wall. It does not require any thickening. Okay. Then the two exceptions are the maximum spacing limitations. This is 1/3 of the minimum plane dimension, would have been 1/4 in the case of a column. And the minimum cross-sectional area of the transverse reinforcement is given by this one equation, whereas in the case of a column, it is given by the two different equations, whichever is larger. Now that equation, as I mentioned, has been brought back by ACI 31814. Now the horizontal shear reinforcement will not do you any good unless it is properly anchored. So typically what we do is provide standard hooks at the end, and then the hooked part development length. So the shear reinforcement has to be fully developed at the face of the shear wall. So the L sub DH distance can be taken from the face of the boundary element. If you are of a more conservative bend, you will take it from the beginning, the outer face of the confinement reinforcement as shown in the picture. Okay, that is probably a better way to go. So we will fully confine the horizontal reinforcement at the outer face of the confining reinforcement. So that distance has to be L sub dh, hooked bar development length, or these days you can go for headed bars, in which case it will have to be the headed bar development length, L sub dt, rather than L sub dh. We have also stipulated specifically that you shall bring the end of the uh, of the shear reinforcement within 6 inches of the end of the shear wall. Okay, so you will bring it out to within 6 inches of the end of the shear wall. The idea is to grab as much compression concrete as you can with these hooked bars. I think that makes a lot of sense. Whether it should be a code requirement or a suggestion, that may be debatable. We made it a code requirement. Now, if you have plenty of room, then you may want to dispense with the hooks or the heads and go with straight bars, in which case you have to have straight bar development length L sub d beyond the outer face of the confining reinforcement, L sub d. Now the end still has to be brought within 6 inches of the end of the shear wall. That still remains a requirement. Now we will allow you to use straight development length rather than hooked bar or headed bar development length, provided this inequality is satisfied. A sub b is the total area of the horizontal shear reinforcement. A sub sh is the combined area of the legs of the confining reinforcement. Okay. F sub y is the yield strength of the shear reinforcement. F sub yt is the yield strength of the confining reinforcement. So this A sub B F sub Y divided by spacing, this is all for the shear reinforcement, must be less than or equal to A sub SH F sub YT divided by the spacing of the confinement reinforcement. If this inequality is satisfied, we will allow you to use the straight bar development length. Now, even when you do not need specially confined boundary zones because your calculated neutral axis depth came out to be less than the critical neutral axis depth, we may have to provide what I'm going to call non-special boundary elements if the local reinforcement ratio at the ends of your shear wall exceeds 400 over f sub y, which is 2.8 over f sub y in your units. Okay, again, even where specially confined boundary zones are not required, we will have to provide non-special confinement if the local reinforcement ratio, and I'll explain what that is, at the ends of the shear wall exceeds 400 over f sub y, 2/3 of a percent for grade 60 reinforcement. Now, when we say non-special confinement, that would mean every other bar laterally supported by a corner of a tie or a cross tie with 14-inch maximum spacing between any two supported bars. That and the non-special confinement will be provided over the length of the shear wall that we calculated for special confinement. So whether it is non-special confinement or special confinement, the horizontal extent of the confinement does not change. It is the same region that we confine. Okay? Now, the maximum spacing of this confinement reinforcement. This is where it is non-special. So you remember it was very tight spacing. It couldn't exceed three different things. The One was the minimum plan dimension divided by 3. Now it is a flat 8 inches, 200 millimeters in ACI 31808. Okay. It will get significantly more complicated in 31814. 31814 says not just 200 millimeters, but the lesser of 200 millimeters and 8 times the bar diameter. Not only that, over this entire length, L sub W or M sub E over 4 times V sub U, whichever is the larger of the two starting at the base, the spacing goes down to 150 millimeters or 6 bar diameter, whichever is the smaller of the two. So it is going to be more complicated in the future, but for now, the spacing of non-special confinement is a flat 8 inches, 200 millimeters. Okay, so that's where it is very much non-special. Now, what is the local reinforcement ratio which exceeding 400 over F sub y will trigger non-special confinement? So we sometimes, this is not often, may have uniformly distributed vertical reinforcement through a shear wall cross section. When it's a lightly loaded affair, there are no significant moments. This is not unusual. Uniformly distributed vertical reinforcement. If that's what you have, then the local reinforcement ratio is the total area of 2 bars divided by the thickness of the wall and the spacing of the reinforcement. Okay, as simple as that. When you have uniform distribution of the vertical reinforcement, it is unlikely that you will need non-special confinement, but you definitely need to check. More often than not, we concentrate most of the vertical reinforcement near the ends of the shear wall because we get more moment strength out of the same reinforcement that way. And it also makes the wall more deformable that way. Anyway, when we have that, so this is the flexural reinforcement. Outside that is distributed shear reinforcement. We have a cover, physical cover this way. We imagine the same cover the other way, where we have a continuous wall. We imagine the same cover. And then we take the total area of the flexural reinforcement divided by the total area of the shaded part of the wall cross section. Okay, if that exceeds 400 over F sub y or 2.8 over F sub y in your units, then we must provide the non-special confinement that we talked about. Okay, pretty much the final item, the horizontal reinforcement. When we have specially confined boundary elements, we talked about how to anchor the horizontal reinforcement. If we don't have specially confined boundary zones, how do we anchor it? So horizontal reinforcement terminating at ends of walls shall have a standard hook engaging the edge reinforcement as shown in the first picture, or edge reinforcement shall be enclosed in U stirrups having the same size and spacing as and spliced to the horizontal reinforcement. So you have to do this or that, but you have to do one or the other, because non-anchored horizontal reinforcement will not serve any purpose. Okay, I have included here two pictures from the commentary to ACI 31814. I have no intention of going into details, and this is not 31808 versus 31814. I want to give you the overall picture, which I think these two figures bring out very effectively. Okay, so when specially confined boundary zones are triggered. The specially confined boundary zone goes up to L sub W or M sub U over 4 times B sub U, whichever is the smaller of the two. Whichever is the larger of the two. Okay? I don't know why I said smaller. So it extends up to L sub W or M sub U or 4 times B sub U, whichever is the larger of the two. It goes into the foundation 12 inches. Okay. So that's the extent of special confinement. Where special confinement is not needed anymore, chances are very high that you will find that the local reinforcement ratio exceeds 400 over f sub y. So now we will provide non-special confinement. The spacing will go from 3 or 4 inches up to 8 inches. Okay? And when we find that the local reinforcement ratio is no longer 400 over f sub y, the reinforcement has decreased because as you go up, the axial loads decrease. When we do not need non-special confinement, we will still provide the regular confinement as in a how do I describe it? Non-seismic column, the regular chapter 10 column. Okay. So that confinement, 12 tie spacing of 12 or 14 inches still has to be provided. So special confinement at the bottom, non-special confinement, and then regular confinement for a non-seismic column. That's what we provide. Now, this figure is where we have used the displacement-based approach. So the trigger is based on neutral axis depth. The next figure is where we have used the conventional approach, but for the point that I want to make, it doesn't make any difference. The point is that we have special confinement and then non-special confinement, and then it is not no confinement, but the confinement that we need in non-seismic applications. Okay. I don't know why this thing. Anyway, okay. So let me then proceed to the last bit. Mechanical and welded splices of longitudinal reinforcement of bounded elements shall conform to the sections that are given. It is 8.2 in your case. Okay, that brings me to coupling beams. Now, after I started this seminar this morning, I thought that I should have included photographs or figures because it is my experience that coupling beams are not always understood. So and I somehow didn't think of it earlier. So when I thought it was too late, coupling beams are, well, think of a shear wall that has door openings at every floor level. The portion above the door opening, the portion of the shear wall between the top of the door opening and the top of the floor, the bottom of the next door opening, is a beam, and that is called a coupling beam. So coupling beams are beams that are linked to portions of a shear wall, or two, we sometimes call them. Okay, so beams linking, let us say, two vertical shear walls, and these beams are typically at every floor level, typically above window or door openings. Now, if the beams are linking special shear walls, then these beams have to be specially detailed. And since I don't remember now which edition of ACI 318, we have very specific detailing requirements for the coupling beams. So the requirements are, if the clear span to total height ratio of the coupling beam, clear span to total height, larger than or equal to 4, your coupling beam is like a special moment frame beam, and you detail accordingly by section 21.5 or 837 in your case. So height to, not height to length, clear span to depth ratio larger than or equal to 4, your coupling beam shall be detailed as a special moment frame beam. If the clear span to total depth ratio is below 4, you may, but you do not have to use two intersecting groups of diagonal bars. You may, but you do not have to use two intersecting groups of diagonal reinforcing bars. However, if the clear span to depth ratio is less than 2, and at the same time, the shear is larger than 4 square root of f sub c prime, now you shall use two intersecting groups of diagonal bars. Okay, and that looks like as in this picture. So when we say diagonal bars, you shall have at least 4 bars. You can have 40 if you need them, but you cannot have 3. And these 4 or however many bars have to be tied and cross-tied like column bars. So when we talk about diagonal reinforcement, it is bunches of bars, 4 or more, intersecting diagonals, and the bars have to be tied and cross-tied like column bars. Okay? In the intersecting area, you will have to be creative because you cannot confine both diagonals. It is physically impossible. But anyway, and there are details given in, sorry, going the wrong direction. There are details given in ACI 318 which are in the picture that I'm not going into. That's a little too much into the weeds for our purpose. Now, I did want to show you that these things have been done. This is the picture of a building that Dick Libby did in Honolulu. He was a practitioner in Honolulu for a long time, but then he retired, and that has been a long time. So this is an old picture and an old building, but it tells you that this is a picture, I would think, from the I don't know, 80s, 90s, something like that. That far back, this was done. Much more recently, John Wallace at the University of California, Los Angeles, has done quite a bit of testing of coupling beams, and these are his pictures. So this is a coupling beam that is on the slender side. You see the diagonal bars in the picture. You also see the extent of confinement around that. This is a far view of the same thing. The point is that the beam is kind of slender, and you see the diagonal reinforcement. This gives you an idea of what the this is a very good picture to give you an idea of what kind of reinforcement we are looking at. And surprisingly, in Dubai, which is not high seismic at all, I have seen worse reinforcement. Like they provide even more reinforcement. I have no idea why. It doesn't make any sense over there, but California, you need it. So anyway, so this is the diagonally reinforced coupling beam, and this is the other way around. This is a short, stocky coupling beam. Okay, the clear span to depth ratio is definitely less than 2. Anyway, so it gives you an idea of what we are talking about, the coupling beams and the reinforcement in the coupling beams. So up until 31805, the only choice our code provided was the confinement of the individual diagonals. But then, based on quite a bit of testing, John Wallace showed that we could provide an alternative where we confine the entire coupling beam section and not try to confine the individual diagonals. So this is shown in the picture. You see the confinement reinforcement, and there are, I will show you better pictures from John. So this is individually confined diagonal reinforcement. This is the only solution that we had under ACI 31805. From ACI 31808 onwards, we have this alternative solution, much simpler, where we confine the entire coupling beam cross section. And you should take particular note of the cross ties going into the coupling beam. Okay, it is so it's I think this picture is very graphic. It is in color. If you follow, if you have an interest, you can see what is being done. Okay, so that is pretty much the what do I want to say? So normally that's as far as you will go. So shear walls. Before I came to the coupling beams, that is something that's basic shear wall design. Coupling beams, obviously, you may or may not have, but if you have them, and it is good to have them in seismic applications, then you now know the detailing requirements. The final thing that that we probably should discuss are the so-called wall piers. Okay? Door and window openings in shear walls often lead to narrow vertical wall segments, many of which have been defined as wall piers in the IBC and in the UBC before it. Wall pier provisions are now included in Section 2198 of ACI 31811, 8368 in your case. I am not sure they were in 31808. I should have, anyway, it doesn't make any difference. You have it in 8368. And so I want to give you also the requirements we have for wall piers. This is fairly recent in ACI 318. It came in either into, I believe it came in 31811. Anyway, so I kind of hesitated yesterday whether to include it or not, because this is these wall piers are a big problem in what is called tilt-up construction, which is very big in California and some other parts of the country. The contractor casts the shear walls on the slab on grade horizontally. Okay, so the wall would be cast on the slab on grade. These are typically big these days they make offices out of them, but they typically used to be warehouses and things. So like not tall and large in plan. So these walls cast horizontally on the slab on grade were tilted up into place, and then uh, obviously you put in place the roof or the diaphragm or whatever you want to call it. Yeah. So and initially these were solid walls, then they started cutting larger and larger openings, and the portions between the openings, uh, they are they are, as in the picture, they are not really walls. Uh, but they were designed like walls. And in earthquakes have an uncanny ability to seek out weaknesses. So when an element like that, because it is relatively thin, is designed with one layer of reinforcement in the middle, it's no question that it will suffer shear failure pretty early on. So this is why we now have specific requirements. Anyway, definition of a wall pier. First of all, the height of the pier from here to there, I think it is marked, yeah. The height of the pier divided by the length of the pier shall be larger than or equal to 2. Okay. If it is shorter than that, then we don't have a wall pier, we have a wall. And the length to thickness into the screen, length to thickness ratio shall be between 2.5 and 6. That is a wall pier. In that range, the element is particularly vulnerable to shear failure. So shear failures of wall piers have been observed in previous earthquakes. The intent, anyway, let me go to the bottom line, what it is that we have done in 318. This is a table from the commentary, which I think explains the whole thing extremely well. So if the height to length ratio is less than 2, this is clear height of vertical wall segment divided by length of vertical wall segment. We were not calling them piers because they may or may not be piers. So clear height of vertical wall segment divided by length of vertical wall segment. As long as it is less than 2, we have walls, irrespective of the length to thickness ratio. If it is larger than or equal to 2, then if the length to thickness ratio is up to 2.5, we have columns. Remember from yesterday, a, there are limitations on column dimensions. One of the limitations was the long side to the short side ratio cannot exceed 2.5. So as long as you do not exceed 2.5, you have a column, and you must design the wall pier as a column. This is a must. Okay, a column, it has to be confined. You cannot have one layer of reinforcement in a column. So the length to thickness ratio below 2.5 or up to 2.5, you have to detail your wall pier as if it is a column, because it is a column. In the range between, so length to thickness ratio between 2.5 and 6, you have a wall pier as defined in ACI 318 BNBC. And then we have detailing requirements, very specific, which I did not reproduce, that are designed to prevent premature shear failure preceding flexural failure. If height to length ratio, not height to length, if the length to thickness ratio exceeds 6, then you have a wall, not a wall pier anymore. And then you will detail this wall pier as a wall. So this is very clear cut, and this is where we have gone in 318. And then something that, so wall pier provisions were in the IBC before and before that it started in the UBC. I believe 94, I think it was 91. Anyway, it was in the UBC for 2 or 3 editions, then every edition of the IBC, but then it did not make its way into ACI 318 until I believe 2011. Now, something that we did not have in the UBC or IBC that ACI has added is shown in this picture. Okay, so if you have a relatively, there is some language, wall piers at the edge of a wall are addressed. Okay, so this is a wall pier at the edge of a wall. Now, if the direction of earthquake force is as shown in the picture, then uh, uh, tension would develop in this sense in the wall pier. Okay, not is it tension or yeah what the compression struts will form. This is a compression force to equilibrate which you will need the horizontal component of that diagonal force will require tension reinforcement at the top of the opening in the wall pier. You will need reinforcing bars like that in order to equilibrate the horizontal component of that diagonal force. If the direction of earthquake reverses, then the diagonal struts will form this way. The diagonal force will be directed this way. Now we will need tension reinforcement under the opening in the wall pier as shown in the picture. Okay, so those bars above the top of the opening and below the top of the opening are required for wall piers at the edges of shear walls by ACI 318. And that is the end of the presentation I planned. Today I am on time, maybe couple minutes before time. So I will take as many questions as I can. Maria has to bring them up for me. Okay, let me see. Okay, first one. Rifat always has a bunch of questions. I don't know if I'll get to anybody else. Let me see. In our country, is common practice is to welding spiral reinforcement with the longitudinal reinforcement in piles. Is it correct or not? We didn't talk about piles yesterday or today, so I do not know why the yesterday I mentioned that if you are going to weld transverse reinforcement to longitudinal reinforcement, it has to be to construction bars. You cannot weld to longitudinal reinforcement that carries stresses by your computation. Okay, so when it comes to piles, I do not know that we have that specific requirement any place, but if you have piles below a building assigned to seismic design category D, I think it will be more sensible not to do the welding. I cannot tell you that there is a requirement against it in the case of piles. I'm pretty sure there isn't, but it probably is not a good idea for the same reasons that it is not a good idea for a special moment frame column. That would be my answer, but I'm pretty sure that there is no specific requirement. Next question, for floor beam design or construction, is it permitted to take different clear cover in a side of a beam. For example, I don't know. I was expecting questions related to what I presented. So I don't. Okay, anyway. So, for example, in a beam, can I use 40 millimeters on interior side clear cover and 75 millimeter on the opposite direction? Huh. So the exterior is exposed, you want to use a thicker cover. The interior is not exposed, you want to use a thinner cover. Again, there is absolutely nothing against that I have seen in our codes. And now that I think nobody has, uh, it definitely is not usual practice, but now that you asked, I think it makes sense. And I do not know of any reason why you cannot have that. Obviously, the uh, minimum thickness requirement has to be honored, and the I would say if the cover is too thick, then there are problems of cracking in the cover and so forth. So you have to be a little careful. But the point of your question is you want to use a thicker cover on the exterior face because it is exposed, a thinner cover on the interior face because it is not exposed, and that I think makes sense. And I do not believe there is anything against that in our codes. For vertical members which axial compressive force is less than S sub G F sub C prime over 10, then to calculate transverse reinforcement spacing according to code, what should be the age of that member? Uh, I'm not. I think the from what I can see in that these are not always easy to follow what is being asked. I think what you are asking is if the axial force is below A sub G F sub C prime by over 10, then your column is like a beam, and then you will provide beam confinement rather than column confinement, and then you would need an H, and an H then would be the cross-sectional dimension of the column. You are asking as the longer side of the member. That will depend upon the no for the it will depend upon which legs of the confinement reinforcement you are designing. For legs in one direction, it will be the long dimension. Legs in the other direction, it will be the short direction. I hope you are following me. But more importantly, I would advise you, and the SEOC Blue Book always said, if you have a vertical member and the axial load is low, still detail it like a column. That is good practice. Do not try to uh, go on the technicality that we now have a beam and we will provide I forget now. uh, there are provisions, I don't remember exactly where, that actually said that irrespective of axial load, the blue book I'm sure said that. Anyway, I can tell you that it is not good practice to uh, not detail a vertical member like a column because the axial load is low. If I am intended to reduce column size or to change column shape, for example, changing circular to rectangular shape in the upper floor than the lower floor in design category D, then where the longitudinal. If I'm intended to reduce column size or to change column shape, for example, changing circular to rectangular, It went back by itself. In the upper floor than the lower floor in SDCD, then where the longitudinal reinforcement can I lap for different column size or different shape column size, because column in design category D didn't permit to lap splicing in just the upper portion of floor level. For the circumstance, is there any elaborate guideline exists? No, there is no guideline that exists, and I uh, why is it jumping back and forth? I don't know. Yeah, this is the one. I bring it up and then it goes back. Anyway, so let me say a couple of things, and I hope you don't take these things negatively. I don't know why you are thinking of these things. If it is seismic design category D, changing the shape of the column along the height is a very bad idea. I I definitely wouldn't do it. I wouldn't contemplate doing it. But more than that, at least in the United States, we cannot do it because formwork. I don't know if you ever thought of these things. Formwork, which stays in place only for a few days, typically accounts, at least in this country, for at least half the cost of a concrete structure, the construction cost, half. Okay, I'm not talking about the building cost, which includes cladding and mechanic. The cost of the structure is typically no more than 1/4 of the cost of a building, and half the structural cost is the cost of the formwork. The formwork gets awfully complicated if you want to change definitely the shape of a column along the height. I've never seen that done. Okay. So, well, when I say I've never seen that done, you go to a place like Dubai where they have money to burn, they do all kinds of illogical things because the owner wants something that looks unique. So I'm not talking about those cases. Sensible, normal people do not do that. The second thing is today we have, so there was a time when, as we went along the height of a building and the axial load decreased, we could only decrease the reinforcement, and the reinforcement cannot go below 0.5% of the actual cross section. But today we can play around with concrete strength. We can use 8 KSI or 10 KSI at the base, go down to 4 KSI at the top. So what is done in this country is, if it is a tall building, we use a combination of high strength concrete, and we go up to 3% reinforcement at the bottom. We taper off the reinforcement. By the time we hit 0.5% reinforcement, we switch to a lower concrete strength and a high amount of reinforcement, and then we taper off the reinforcement, then we go down to a lower concrete strength. We never change the cross section because that is cost prohibitive. The formwork gets complicated. Okay, so do not. My advice is, do not do the things that you are thinking of doing. That is not cost effective, and changing the column size design category D, I would not necessarily say that it is detrimental to performance, but at the same time it doesn't enhance performance. And your particular question of the requirement of splicing only at mid height of the column, that never goes away, no matter what you do, how many transitions, whatever. Okay, to bring that back. In coupling beam, what should be the minimum and maximum bar diameter limitation? There are no separate bar diameter limitations for coupling beams. Whatever is for concrete construction applies. Although one thing I will add is the diagonal bars have to be developed into the wall piers, and many times you do not have a lot of room. So you may be forced to use thinner bars for that reason, but there are no bar diameter limitations. How to place hoops in the intersection of diagonal rebar? What is the procedure? There is no set procedure. As I said while I was presenting, you have to be creative, and the picture that I showed you shows one way out. Go back to the picture. It keeps on jumping. I don't know what the heck is happening.
Try clicking on the question, maybe it'll stay put.
So the question, the end, it says, I think it's a hard task. I don't know about hard. It has been, as I keep on saying, it has been done, but you have to do the best you can. Confine that area rather of the intersection rather than the individual diagonals. That's the key to the whole thing. If a pier thickness is too thin or coupling beam diagonal bar have not enough space to ensure development length in the pier, then how to solve this problem? You have to have room. This is not a question of solving a problem. If you don't have room, the solution isn't working. You have to go to something else. I think number 8, diagonal rebar have not enough room to ensure development length in 12-inch pier. So yeah, I agree with you. You will need a minimum of 14 inches for number 8 bars. I know that for a fact. Okay, minimum 14 inches. How to solve this? This is how you solve it. You go for a thicker wall, and you will need room horizontally as well. So not everything will always work out. You will have to. This is a good example. You provided your own answer. Number 8 bar in so a 4 number 8 bars making up a diagonal will not work in a 12-inch section. I totally agree with you. 14 inches is the minimum. I know this number. Okay. Are seismic foundation provisions being only applicable for design category D only? I think there are no guideline for SDCC or less. That I didn't look into the foundation provisions of BNBC, so I cannot tell you. In the US, the foundation design provisions are in the IBC. IBC as a whole, Chapter 18, that you should look into for foundation design provisions. In addition, ACI 318 in the seismic chapter, which was 21, is now 18, has a section on foundations underneath buildings assigned to design categories D, E, and F. So if you have foundation underneath a high seismic design category building, then IBC requirements apply, ACI 318 requirements also apply, and you if there is a conflict, IBC requirement will prevail, not ACI 318. Okay, so that's the way things are in the UBC. It is not that there are no requirements for SDCC or less. Those requirements are in the IBC. As I said, I haven't looked into what BNBC has done. Professor Abedin or Professor Ansari will be able to tell you those things. And now that the question has come, I'm curious. I will look. But that's your answer. There are requirements, and if you think what kind of requirements are used, go to whatever IBC edition you can get hold of. And I should also tell you that starting with 318.14, we have started bringing those requirements into ACI 318. So if you go to 318.14, you will see a lot of requirements. 318.19, you will see even more. Let me no, let me no, I didn't say the right thing. In 318.19, we brought many of the foundation requirements into ACI 318, and you will see more in 318.25, which is being worked on right now. Okay. Yeah, let me see another couple, because this is the first one that is not from Rifat. If there is a structure having different frame system, there will be different R values. It is wise to consider the lowest R value during earthquake analysis. If we want to consider the actual R value, is it possible to calculate the R value by pushover analysis or other method? No, this I covered in one of the earlier lectures. If you have a combination of structural systems in the same direction, then you have to use the lowest R value of the systems that are strung together. This is a code requirement. This is in ASC 7, this is in BNBC. If you have different structural systems in orthogonal directions of a building, then the two orthogonal directions are kind of independent. If you have moment frames in one direction, you design that direction for an R of 8. If you have bearing wall system in the orthogonal direction, you design the orthogonal direction for an R of 5. It's as simple as that. Okay. So there are specific code requirements, and you cannot, when there are code requirements, you cannot, unless the code gives you permission to supersede those by doing some kind of analysis, you are not allowed to do that. Okay. What will be the configuration of boundary element for T and L type shear walls? Would you please provide some reference to design? I covered that. Remember, the entire effective flange width is part of the confined boundary zone, and you go 12 inches into the web from the intersection of the flange and the shear wall. This is true of T sections. This is true of L sections. So I think I went over it. If you, I don't remember now. Go over the slides and you will find the answer. Do we need to provide tie with seismic hook for longitudinal bars of shear walls? Do we need to provide tie? Don't quite understand the question. Do we need to provide tie with seismic hook for longitudinal bars of shear walls? I don't know what you are asking. So in a shear wall, the whole, not whole, but much of the discussion was that we may or may not require specially confined boundary elements. If we require specially confined boundary elements, then there are very specific confinement requirements that we went over. Those are not ties with seismic hooks. Those are hoops with cross ties that would be required around the vertical bars in the specially confined boundary zones. If we have to provide non-special confinement, then there are requirements that you can look up. Now, the remainder of the shear wall has vertical shear reinforcement, distributed shear reinforcement, as we call it. Those do not have to be confined. We do not need to confine them. We do not confine them, although very lately in 318.19, we require cross ties going through the walls, but you don't have to worry about it. I hope that answers your question. So the Boundary zone reinforcement has to be confined like column reinforcement. The distributed shear reinforcement doesn't have to be confined. Next question, increase of building structure. May we assume it as cantilever shear wall because top of shear wall semi-fixed joint but top of building is free? I unfortunately do not understand this question at all. This is exactly what it reads. Increase of building structure, may we assume it as cantilever shear wall because top of shear wall semi-fixed joint but top of building is free in translation and rotation. Unfortunately, I cannot understand, so I cannot answer that question. Let me see. Assume there is an existing building which is designed as ordinary moment frame constructed in 2014. If we follow BNBC 2020, the building should be designed considering intermediate moment frame. Even in 2014, you could not do ordinary moment frames, so I don't know. If we want to assess this particular existing building, what should we consider as the detailing is lower than required? Okay, so if you have an existing building, whenever it was built, and you are assessing it, and you find that the detailing is ordinary, whereas you should have used intermediate or special detailing. There are basically two ways to approach such problems. To provide detailing after the fact is very expensive, and also it disrupts whatever activities are carried on inside that building for extended periods of time. So one way to fix these buildings, if that's the right word, is to make them very rigid by uh, providing new shear walls or something like that, or bracing of some kind. So this is a topic unto itself. I cannot give you a generalized answer, but when detailing is deficient, you either have to bring the detailing up, which is an expensive proposition, or more often than not, we try to brace it such that the building will be so rigid that it will not deform much in an earthquake, in which case the deficient detailing should still be sufficient. So the next question or suggestion, whatever it is, please repeat the explanation of R, detailing, and strength level. So the not explanation, what I said, and this is probably not a bad thing to end with. Seismic design is an exercise in trade-off between strength and inelastic deformation capacity. And inelastic deformation capacity comes from proper detailing of the structural members and joints. We have three levels of detailing: ordinary, intermediate, and special. Okay. So we can go for a high strength level and ordinary detailing, or a lower strength level and intermediate detailing, or an even lower strength level and special detailing. But I also pointed out that, well, before that, your specific question. So this, when I say we can design for a low strength level and special detailing, or an intermediate strength level and intermediate detailing, or a high strength level and ordinary detailing, the strength level is set by the design base shear that we use in design. The expression for the design base shear has an R in the denominator. If the R is large, we are choosing a low strength level to design for. If R is small, we are choosing a high strength level to design for. So when R used in design is large, we have to do special detailing. When R used in design is small, we are allowed to do ordinary detailing. If R used in design is in between the two values I talked about, then we are allowed to use intermediate detailing. Okay, so that is the role of the R value. R sets the design force level, and depending upon the design force level or the R value, we will be required to do ordinary, intermediate, or special detailing. Okay, so that was essentially the discussion. Is something related, sir. We will take R value of 8 in case of special moment frame, but we will take R value of 7 in case of dual system with special moment frame. Here, my question is that why does R value decrease in dual system? This is a very, very good question. We will take R value of 8 in case of this is an excellent question, and I do not have an equally good answer. Uh, this is an excellent question, and I do not have an explanation except that an R of 8 for a special moment frame goes back a long way, and I guess that we didn't. Let me look into it, think about it, and if I have something that I can come up with, I will share it with everybody. This is definitely one of the best questions we got in all the seminars. Okay, so that's not a bad place to quit for the day. It's a quarter after the hour, uh, and I think, yeah, and there are at least twice as many questions as I have been able to answer, which has been the story all along, and I do not know what to do about that. Anyhow, so thank you very much for attending. I think today things went smoothly. That's my observation. Hopefully you have gotten quite a bit out of the whole thing that I tried to. So I tried to do seismic design, the force part, in 2 different seminars, and then the detailing in 2 different seminars, frames and shear walls. If you attended all 4, you have been exposed to pretty much all facets of seismic design by BNBC. Obviously, there is a lot more that can be discussed, but we have only so much time and so forth. Okay, thank you very much. The training will continue, as you know, until the end of July, but I believe that this is the last time that I will do one of the seminars. So I thank you very much for your attendance throughout these seminars and the questions. And we will see if we can find any way of answering these questions. Thank you.